during spring sync for pipe course, right?
I think last year, I don't think I've made it to an actual spring thing in a couple years because we've always had scout campouts on that weekend. But I should be able to make it this year.
Yay!
I'll say, but because my kids were in scouts and that was always like the scout weekend, or it's like during esports state finals or something.
Yeah.
All right, let's take a look at this one. Trying to get this as condensed as possible. What should we do first? Our coefficient should go up and become power. Absolutely right. We want to get this all the way down to a single log if possible. So we should take all of our coefficients and put them up as exponents. So I'm going to take this 3 up as an exponent here. Don't know why I changed colors. My 2 as an exponent up over here. So we're going to have our log base 9 of 3x to the third. Like this. It's that whole term that's getting that power on it. And then we'll have our log base 9 of our y to the 5th then squared. And this guy didn't change.
Can we simplify?
Mm-hmm. Yeah, this is probably going to be easier to do the next bit if we simplify this a little bit. You don't have to. You can simplify at the end. But if you want to simplify these powers here, that is 100% a valid way to go. So if we want to simplify these powers right here, we're going to have our log base 9 of 3x cubed would be our 27x to the third. So 3x, the quantity cubed. And then log base 9. What do we get when we have y to the 5th squared? Y to the 10th. Good. And then our 3x is just kind of falling down again. Cool, cool. Good thought. What should we do next? Addition becoming multiplication. We can absolutely do that next.
Is it okay that I simplified and did the
Yes.
additional multiplication?
Yeah, if you combine these into more than one, combine a couple of steps together at the same time, that's totally fine. So if you did the simplification at the same time we did this, we should wind up with the exact same statement. Log base 9 of multiply these together. Our 27x cubed y to the 10th. Minus log base 9 of 3x. What do we do next? Yes, our subtraction is going to turn into division. So we're going to have our log base 9, and we're going to wind up with a fraction here, where our numerator is what was on the left, our 27x cubed y to the 10th, and what's in our denominator is what we were subtracting by, that 3x. So we've gotten this down to one single log. Can we simplify that?
Yes.
Mm-hmm. So we got it down to one log, but then we can simplify, because we want this as simplified as we can get. It'll make our lives easier. So our log's not going to change. Log base 9. What will this simplify down to be? 9 x squared y to the 10th. Because the 27 divided by 3 are x cubed divided by x. The y's aren't changing. So if we have more than one of the same letter, we need to try and simplify it as much as possible. Okay. Questions on that one with our condensing? Because expanding works the same way, just in reverse. Usually pretty good with that one. I want us to do a little bit of solving, and then we're going to do some graphing today. So we're going to do a couple of solving problems like this. So we've got 3 log base 2 of x equals 2 log base 2 of 3. Here. Kind of gross. Yeah, I would absolutely start this the same way we did the last problem, where I try and condense these as much as possible. I would like to get these coefficients off here, because ew. So we can put these up as powers. Absolutely valid. I can take this 3 and put it up as a power. I can take this 2 and put it up as a power. That is absolutely valid. So I can rewrite these as log base 2 of x cubed equals our log base 2 of 3 squared, or 9. What can we do here? Because now we have the same base on these logs and there's nothing else going on, so I just need to set my arguments equal. The bases are the same. I don't have to do anything else to them. I just need to know, when does my argument of x cubed equal my argument of 9? Their bases are the same. I put my stylus down and I'm 4 seconds away from my iPad. There it is. So what we can do is we can look at these 2 arguments and find out, when does x cubed equal 9? How do I get my x? Cube root both sides. Do we know the cube root of 9? So do we know the cube root of 9? No. Cube root of 9. Or you can put 9 to the 1/3. Also okay. As long as that doesn't give us a negative base, we are fine. I did make a mistake when I was talking yesterday because I had mixed up my grad school class where I'm working in the imaginary numbers instead of here. We don't want to have negative bases. Absolutely still true. We also don't want to have negative arguments. That's the other thing we're checking through. I misspoke yesterday because in my grad school class we're in the world of imaginary numbers, and then in case we can have negative arguments. But when we're checking, we're going to make sure we have no negative arguments, no negative bases. That's how we check. So just clarifying that from yesterday because I did misspeak. So I just want to make sure we're 100% transparent. I own that one. That's on me. I said it wrong because I got confused. But here, our x is in our argument. This is a positive number. Square root or cube root of 9 is a positive number, so we do not have a negative argument. We do not have a negative base. So this is a valid answer. That's our full solution here. Yay, we did it. Go team. We're going to do another one just because I want us to practice another one. So we've got log base 4 of 3x plus 2 equals log base 4 of 7 plus log base 4 of 3. what should we try and do here? Addition becomes multiplication. Condense this side. I see logs with the same base on both sides, so I'd really like it if I could just have a log of something equals log of something, because then I can ignore the logs entirely and just look at my arguments. So I'd really like if we could condense this right-hand side down. So we're going to take our addition and turn this into multiplication. So we're going to condense it. So this is going to equal our log base 4 of 7 times 3. Addition becomes multiplication of the arguments. Whenever we're condensing, we should lose logs. So the left-hand side I didn't change, so my iPad's deciding to jump places. Fun times. So our addition becomes multiplication. So what that tells me is we now have our log base 4 of 3x plus 2 equals log base 4 of 7 times 3. Well, 7 times 3 is just 21. So again, you don't have to write these as separate steps. If you combine some of these steps that I write down together, that is absolutely okay as long as you give me some steps. I don't care which ones. Just give me like at least a couple. Other than that, if you start combining things together, I am totally okay with it. Just don't teleport directly to the end. Give me something to prove that you did it, not your phone. Because once we have it here, what can we do? Set our two arguments equal to each other. We have our 3x plus 2, this argument, and we want to know when that's exactly the same as this argument here. So we want to know when our 3x plus 2 equals 21. So how do we solve this? Minus 2 from both sides. So 3x equals 19. Divide by 3. What's our solution? 19 thirds, or 19 over 3. 6 and a third, if you're really into mixed numbers. That x value, if we look back at our original function, this x of 19 thirds does not give us a negative base or a negative argument, so it is valid. So we check to make sure we don't have a negative base and we don't have a negative argument. If we have a negative base or a negative argument, that solution is extraneous. So no negative bases, no negative arguments. Questions on the solving stuff? Because the last thing we got to do with our logs here is graph it. Yes, dear. Okay, cool. I recalled saying that negative arguments will happen sometimes. That's only when you're in grad school and confusing real numbers and imaginary numbers. So I just wanted to make sure it was real clear, because in my head I said it wrong. And I would rather correct myself too many times than not say it the right way. Just because nobody likes to admit to be wrong, but I was 100% wrong. At least in my head. Okay, questions on this one? Because our last thing we need to do is to graph some logs. So I have gabillions of graphs. We are going to do at most 4. So I'm going to pass out some graphs. You can use whichever ones you like, whichever ones you need, whichever ones you choose. So I'll pass out some singles and I'll pass out some sets. If you like singles, use singles. If you like the sets, use the sets. I don't really care. But we're going to graph some logs. We're going to do some transformations on logs. Any extras that you guys have of graphs, you can leave on the tables for next period. That's also going to be doing it. Because some people like them in 2s, some people like them in 3s, some people like them in 1s. Or we'll cut them apart. And honestly, I have them all, so I'm like, might as well get them all out, and then I just clean them all up at the end of the day. And it gives me less confetti because I know that you guys use a shaky drum. So I have lots of options. I can always get you guys more. If you run out, let me know. I don't think it's probable with the number of graphs I just handed out. I think I just handed out like 200 graphs. Yes, sir. Yeah, absolutely. Yeah, if you guys ever need different scissors or glue, let me know because the buckets all get mixed. So they wind up chaotically scattered. Wait, we're okay. And some of those glue sticks are at least 2 or 3 years old, so. Okay. Appreciated my school spirit. It is 90,000 degrees. The hoodie is cute, but very, very hot. I love it. It's my cat's most favorite.
Does the cat like to hide in the pocket?
No, but if he sees me wearing it, he will yell at me until I sit down and he sits on me.
That's so cute.
Until you realize he's 25 pounds and he's very heavy. And he yells like a grumpy old man. Meow. Meow.
What's his name?
Roy. Because Siegfried was too weird.
His boy?
Because Siegfried was too weird. He's an all-white cat, like a white tigers. Siegfried and Roy, they're magicians in Vegas. They were, until the white tiger attacked one of them. They were very famous for having white tigers in their circus act in Vegas. All right. So we're going to graph our basic log first. This is kind of our parent function when we're dealing with logs. Just like with exponentials, each different base kind of has its own parent function. So we have to use the base of the log to help us get there. For some of us, we're going to need to draw 2 tables for this one. Some people will be able to do it with 1. I don't really care which way you do it. I'm going to draw it with 2 so we can see what's happening. Because when we're making our tables for logs, for the most part, we are not really going to be thinking logs because log base 2 of a number being a decimal is going to be gross. So what we do is we use the fact that logs and exponentials are inverses of each other. So if we think about, instead of log base 2, the inverse of it, 2 to the x. I'm going to make the table for it. I'm not going to graph the picture. I'm going to just make the table of 2 to the x. That's where we picked our x's and found our y's. And we use that good view of the middle, our -2, -1, 0, 1, and 2. And I'm going to put that through 2 to the x, my base of my log. That's why I picked a 2. So 2 to the power of -2 gives us a 1/4. 2 to the power of -1 is 1/2. Anything to a 0 power is 1. 2 to the first is 2, and 2 squared is 4. Our exponential functions had asymptotes, horizontal asymptotes at our y equals 0. So I'm going to put that down there as well. So this is kind of like where I think of the birthplace of log base 2. It starts as 2 to the x, and then to get the table for our log, we want to take the inverse. So everything that was an x becomes a y. Everything that was a y becomes an x. So we're going to straight up flip the 2 columns. Anything that was an x becomes a y. Anything that was a y becomes an x. So we're going to have our, I'll move this up a line just because otherwise I am super close to the bottom. Log base 2 of x means I'm going to take everything that was an x and put it in the y column. And everything that was a y goes in the x. So we're going to have our -2, -1, 0, 1, and 2. And we're going to have our 1/4, 1/2, 1, 2, and 4. There we go, just moving that up. And then also for my asymptote, I can do the same thing. We had our asymptote at y equals 0, but anything that was a y becomes an... Holy cow, that was loud. That's why I haven't gotten an email since announcements and forgot to turn my volume down. There we go. So our asymptote is going to happen at x equals 0. So when we go to graph our log, we don't need to graph 2 to the x. I'll sketch it up here after we graph our log so you can see what it looks like. But this is what we're trying to graph here. So our asymptote is going to be at x equals 0. We've gone from having a horizontal asymptote to a vertical one. So we're going to have an asymptote right here at x equals 0. That is the inverse of our exponentials asymptote.
How do you get that asymptote?
When exponentials, we had, there was absolutely no power I could put on 2 that would get me below 0. So we had that asymptote at y equals 0. We could never go negative here. Anything that was a y becomes an x when we take our inverse.
Every single time.
Whenever we take an inverse, everything that was an x becomes a y, everything that was a y becomes an x. That's why these two columns flip-flopped.
And the asymptote is always
With no transformations, yes. When we start doing transformations, that's when we'll have some shifts. I'll show you. We're going to practice it. So then what we're going to do is we're going to plot up our points. We have 3 points in this little space right here. We've got our x is 1/4, our x is 1/2, and x is 1. So they're going to be real close together in this little spot. So just be really careful. Because we have our x of 1/4, which is, oh, my table's not here. There we go, -2. So right about there. Our x of 1/2 is at -1. So right about there. As long as it's like within that square, we're fine. I'm not going to be like, you see that's 1/2. I think that's closer to 1/3. I'm not that petty. As long as it's kind of there-ish, think of it as if you could draw a big dot and it would be in the right spot, you're in a good spot. So if your dot was chunky and it covered enough space, it would do the thing. So as long as you don't tell me that it's, over here or like back there, or way down here, like, fine. Get it close, call it good, and move on with our life. So then we have our 1, 0, 2, 1, and 4, 2. So this is what our log base 2 of x looks like. This is our inverse of that 2 to the x. I'm going to sketch the 2 to the x up here fairly light so we can see it and see what we're looking at here. Oh, skinny dots. This would be that exponential function of 2 to the x. And we can see that these are inverses of each other because I could diagonally fold them and get them to line up. They're reflected over the line y equals x. That's what inverses are going to look like. They look like they're just diagonal folded onto each other. We're not going to have to draw the original parent function. We shouldn't have to put that on there, but I just wanted us to see what that looks like. I'm not going to ask you to graph an exponential and a log at the same time because it makes your brains hurt. So this is what our graph should look like. This was just us talking about the exponential. But that's what our graph should look like. When we're working with logs that have transformations, we're going to start the same way. We're going to make our 2 to the x, or our base to the x, to switch around to our parent function for our log, and then we'll apply the transformations. So some of us will write only this table in the transformations and can put the exponentials in kind of in backwards, where you write these and then these. Or if we want to write all 3 tables, that is also totally valid. When we're looking at graphs, I look at your picture first. If I can't figure out what's happening on your picture, then I'm checking your tables. So the tables are a tool for us to use. I am almost never grading the table itself. Not for plotting points. Questions on this one? Okay. Let's do a transformation. So we're going to start with a simple one. There we go. When we look at logs to find all of our pieces for those transformations, we are occasionally going to see B transformations again, not base B, but when there's a multiplied inside, multiplied against A, or sorry, multiplied against the X. So I'm putting that into, so I'm going to put our kind of generic with a log base 2, so we don't have B's that mean 2 different things here. The base on this tells us our parent function, so it is not a part of a transformation. We can have those B transformations on there. Not going to be a super common thing we see, and we're not going to see a B and an H at the same time in logs because we're mean, but not that mean.
Is the log,
It won't always be log base 2.
okay, that's the right question.
But between our exponential, our parent, and our graph, the base won't change. So I put this as a base 2 so that we could talk about the B transformation. That's our 1 over B that we do times X.
Oh.
We did them back in like rationals and last chapter, but I know it's been a second, and that was like a new thing then. So when we're trying to graph these, especially this one where we don't have a B, everything here is familiar pieces. We have A, we have H, we have K. H always has that opposite sign. So our H is inside the parentheses with the X. K is on the outside. So we have here, our H is going to be 4. So we do expect this function to move to the right. We have our K of a positive 1. To do these graphs, for our logs, what we're going to need to do is we're going to need our base to the X, so 2 to the X is going to be basically our parent. We've already made the table for 2 to the X. We used that in the last 2 of them. Or the last one, because we've only done one graph, because my brain is so good. We love my brain. My brain is fun and makes interesting choices. We did our 2 to the X. That's our -2, -1, 0, 1, and 2. With our Y values of 1/4, 1/2, 1, 2, and 4. That has an asymptote at Y equals 0. Again, we don't need to graph our 2 to the X. It is a tool for us to use to get the parent function for log base 2 without having to go, what the heck is log of -2? Because logs are decimally and kind of gross. So we're also going to grab our parent function for log base 2. This one we are also not going to graph. We're only going to graph our transform function, but we need our log table to be able to do the transformations. because this is the real parent function of our graph. And all we need to do between our 2 to the x and our log base 2 is to take these two columns and switch them. So again, you don't have to write your 2 to the x if you don't need to. If you can come through here and go, well, that would be our -2, -1, 0, 1, and 2. That would give us 1/4, 1/2, 1, 2, and 4, and just fill in your columns backwards. That's totally okay. You don't have to put that information there. Logs have asymptotes where x equals. So our asymptote also switches to an x equals. To do our transformations, our transformation table, that's when we take our y times a plus k, because graphing makes us yak. And we've always done before x plus h, but if we have our b transformation, not the base, this b here, if we have a b, that's when we had the 1 over b, the reciprocal of b. We did it ages ago, it's been a hot minute. So if we have a b transformation, we do 1 over b times our x.
How would you know if you had
If it was like 2x.
oh.
Or 3x in here. So log base 2 of 3x. Log base 2 of 7x. That would be the b here. Or log base 2 of 1/2 x. So we're not going to see tons of those, but I wanted to mention it.
If it was a fraction, would you flip it again?
Mm-hmm. Yes. Yes. So we don't have a b transformation here, but if we had a number in front, that's what we do with it. So all we have is our h of 4 and our k of 1. So we don't have an a transformation here either. So we can use our parent table here to make these transformations. We can apply these transformations also to the asymptote here if you don't want to have to think it manually. So we can take our x and put it through these transformations. So I'm going to take all my x values here plus my h. So we're going to add 4 here. I don't have a b transformation, so it's nothing's going to multiply. So 1/4 plus 4, and we get 4 1/4. 4 1/4. 1/2 plus 4, we get 4 1/2. 1 plus 4 gives us 5. 2 plus 4 gives us 6, and 4 plus 4 gives us 8. Our asymptote, we've got x equals 0, so I need to take that and add 4. So our asymptote's going to happen at x equals 4. Because it's an x. I can put it through that same x transformation. 0 times 1 over b, still 0, plus 4, plus h. Our y's, we do the same thing. My -2 times 1, because I don't have an a here, plus k, plus 1. So we're going to have -1. -1 plus 1 gives us 0. 0 plus 1 is 1. 1 plus 1 is 2. And 2 plus 1 is 3. So we get our points here to plot up.
Is the asymptote at x equals 4?
It is exactly at x equals 4.
How would you tell that by the equation after the graph?
It would be our h. So you can also think of it as it was an x value here. I can run it through the x transformation. It's going to do the exact same things. So my 0 plus 4, you get 4. So you can run it through the transformations. That's true when we have transformations with y asymptotes as well. You can run it through your y transformation and it'll do the same thing. So when we plot these points, I'm going to put my asymptote up here. That is not what I meant. I want that to be slightly see-through. Well, it's chunky, but it's there. And then we're going to plot our points. 4 1/4, -1. 4 1/2, 0. 5 1. 6 2. And 8 3. So we get a function that looks like that. Okay? Yes, dear. If it's structured like this, it would still just be the H. So the B is taken out kind of like a GCF. For the most part, I don't think we give you any that's both going to have a B and an H at the same time, because that's a lot. Let me double check real quick, because I don't think. No, it will either have a B or an H. I'm not going to have both. I don't think. Ever. Yeah. It's only going to have a B or an H at the same time, never both. Just because logistically it's obnoxious. Okay, so if we had something like, we're not going to do the whole graph, but just to see it, something like this where we had a power on the top. If we had log base 3 of x plus 1 squared, I can use my log properties. This power comes down to be a coefficient, and the power becomes an a value. So this would give us an a of 2 with our log base 3 of x plus 1. So the power properties, all those condensing things, can still come into play. If we have an exponent on our argument, we don't need to multiply it out. I can make that be my coefficient and use it as a vertical stretch. So the powers can be involved in this to give us a values. That's pretty much the only way we're going to see those used. And if we have a b, we're going to use that as a transformation on there. Okay? The graphing stuff is the last part of 5.5. That is as far as we needed to get. We have 3 minutes.